Hello, I'm Ryan Rogers, and I'm here to talk to you about joint work with my colleague Mark Cesar on unifying privacy loss composition for data analytics. And this is work done at LinkedIn. So first, we're going to be using differential privacy. So here's the definition of it. It was introduced by Dwork et al. About 15 years ago, and it's a property of a randomized algorithm. So we say an algorithm is going to be differentially private with some parameters if for any two neighboring data sets, these are data sets that differ in at most one person, the output distributions of this algorithm are going to be similar to one another. And when I say similar, this is precisely what the parameters quantify. We say that epsilon is the privacy loss, and the smaller it is, the better for privacy. And delta is this sort of correction factor that allows for more flexibility in the algorithms we create. So when delta is equal to 0, we say pure DP, and otherwise we say approximate DP. So one of the very nice properties about differential privacy is that it composes. So what does that mean? That means that I can take simple differentially private algorithms and put them together and make a sophisticated algorithm, and the privacy analysis is straightforward just by analyzing the private subroutines. So just to give you a little bit more information here, if I have multiple differentially private algorithms with some privacy parameters, then the compose algorithm, this is the algorithm that sort of takes the results of all of these differentially private algorithms, is going to be global differentially private with some privacy parameters, epsilon g and delta g. But then the question is, well, what are those parameters? So we can apply basic composition, which says we can just add up the privacy parameters. So just add up all k if we're composing k many differentially private algorithms. Advanced composition allows us to get improved privacy loss composition bounds. So think of it here as like privacy loss degrades with square root k rather than k. And we can also just compute the optimal composition bounds. So if the only information I have is that I'm composing differentially private algorithms, this is the best composition bound that you can get. And the formula is pretty complicated, but for the homogeneous case, when epsilon I is equal to the same privacy loss parameter, then we have a formula for it. But in general, this is hard to compute for the heterogeneous epsilon case. So what about specific mechanisms? The previous results work for any differentially private algorithms, but usually we're dealing with very specific algorithms. So in particular, the Gaussian mechanism is a mechanism that just adds Gaussian noise to an aggregate statistic, and we can use better analysis tools to get better privacy loss composition bounds. In particular, using concentrated differential privacy introduced by Bunn and Steinke, is both it gives a simple composition bound, and that's also tight, sort of the best you can do with Gaussian noise. And then we can always convert that back into an approximate DP guarantee, going from ZCDP to approx DP. Then there's also the Laplace mechanism, which is very common in differential privacy, which adds Laplace noise to the statistics, or we can use randomized response. And you can think of these mechanisms as sort of being the worst case pure DP mechanisms. So this is sort of what the optimal composition bounds are for. So we can apply optimal composition to get a very good privacy loss composition bound. Another approach is to take the privacy loss parameters for DP and convert that to ZCDP, and then do composition there. And then spit back out to approx DP. The issue there is that the conversion of epsilon DP to concentrated DP is lossy, so you're going to lose some factors there, and would be better to just go directly with the optimal composition bound. There's also a class of algorithms called exponential mechanisms, which were introduced by McSherry and Talwar, and these ensure pure differential privacy as well, but it was shown recently that this actually satisfies a stronger property called bounded range that implies differential privacy, but we can actually get better ZCDP parameters than just simply going from DP to ZCDP. We can go directly from bounded range to ZCDP. Also, in prior work, we showed that we can actually compute the optimal bounded range composition bounds to get an approximate DP guarantee. So with this knowledge, we then ask the question, well, how do we compose algorithms in the best way over these multiple classes of mechanisms? So the practical setting here is where we have some analyst that wants to interact with some data set via a differential privacy system. They ask some query, and the DP system is going to return something with, say, the Gaussian mechanism. Then a new query comes in, maybe runs the exponential mechanism, and then another query is going to return the Laplace mechanism. And so just to show that this is actually a practical setting, for mechanisms like top K algorithms, we typically do this in a two-phase approach where we first use exponential mechanisms to discover the elements that are in the top K. Once we have those elements, then we want to add noise to them to return noisy counts of those top K elements. So then we apply Laplace mechanism, or you can apply Gaussian mechanism. So sort of combining the two, we really want the best possible composition bounds that utilizes multiple classes of mechanisms. Okay, so one way that we can combine these mechanisms to get an overall privacy loss composition bound is we can convert everything from their class into a ZCDP bound, and then do composition there and ultimately get back to approximate DP. However, this is going to lose the benefit of, for differential privacy, using directly the optimal DP composition bounds to get an approximate DP. Or if we're using exponential mechanisms, this is also going to lose the benefit of just being able to apply optimal bounded range composition bounds. Another question is, can the ordering of how these mechanisms were selected from these different classes impact the overall privacy loss guarantee? Note that if we're doing everything with ZCDP, all of these are going to have different ZCDP parameters. So does the ordering matter in how we're selecting these mechanisms? So for that, we introduced something called Setwise Composition, which, just to give you a very specific example, consider a system that allows K many queries, so K private queries, and it's enforced that K minus M of them are going to be bounded range or exponential mechanisms, and the remaining M of them are going to be epsilon DP, right? So maybe Laplace noise mechanisms. So to get the overall privacy loss bound, what we can do for such a system is, well, let's convert everything to epsilon DP, right? So now it's just composing K many epsilon DP mechanisms. It's in the homogeneous case, all the privacy parameters are the same. So I can apply optimal DP composition there. Another approach is to convert everything to ZCDP. This is going to ensure that you get the benefit of using bounded range composition bounds because it leads to a slightly better ZCDP parameter. But traditional differential privacy composition bounds do not allow for adaptive orderings of parameters. You have to sort of fix the ordering of parameters in advance, and then the mechanisms within each class can be chosen adaptively, but the ordering of classes of mechanisms needs to be fixed. And so we show that, in fact, you can actually use the traditional composition bounds when you allow this adaptive ordering. And so that allows us to then compare these two options, option one and option two. So the black curve in the middle is showing you what happens if you use option one. So convert everything into differential privacy and then do optimal composition bounds there. Option two are going to be all the other curves, where I'm going to change the number of exponential mechanisms. So if I just make everything or just eliminate all exponential mechanisms and just going to use differential privacy, obviously option two is going to be worse than using option one because I know that I can't do better than optimal composition for that case. So this is comparing the top curve with the black curve in the middle. However, if I know everything is an exponential mechanism, then I should not use optimal composition bound. And in fact, using this easier composition with ZCDP will lead to better overall privacy laws. And so the takeaway message here is that you approximately, if half of your mechanisms or more than half of them are exponential mechanisms or bounded range, then we can improve over optimal DP composition by utilizing the ZCDP composition bounds. Okay, but then I wanted to talk, explore the idea of, well, what about optimal composition that combines both differential privacy and bounded range? So what is the best composition you can do if you know sort of in advance, this is the number of exponential mechanisms I have, and this is the number of differential privacy mechanisms I have. So with prior work, we know that if everything is in differential privacy, then we have the optimal composition bounds. We also know from prior work that if everything is bounded range, everything's exponential mechanism, then we also have optimal composition bounds there too. But there's a distinction between these two settings, which matters with bounded range, but does not matter with differential privacy. And this is the setting where either the analyst gets to select the queries non-adaptively, so selects all the queries in advance and just asks them all in a batch, versus the adaptive setting where the analyst gets to see the results of each query and then decide on a new query based on that. And so in the two settings here, we know that optimal differential privacy composition bounds, these two settings are identical. There's no difference between the privacy loss that we get in both of these. But for bounded range, the story is different. So these two settings are actually different, and we know this from previous work. And so because of that, we want to then explore, well, what is the non-adaptive optimal composition bounds when we're combining both bounded range and differential privacy? So let's focus just first on the homogeneous case. So everything's going to have the same privacy parameter. So epsilon I is equal to epsilon for all of them. If everything is known to be differential privacy, we know that we can compute the optimal privacy loss bound in linear time. Based on prior work, where K is the number of mechanisms that we're combining. We also know that we can compute the optimal composition bound for bounded range mechanisms in order K squared time. But if we want to combine the two, then we can do it in cubic time. And just to show you the extremes here, the top curve is giving you optimal DP bounds, and the bottom curve is giving you optimal bounded range bounds. And then we can interpolate the number of exponential mechanisms in between. Just due to time, I'll then skip to the end. Thanks.